Hello, I'm Chris Richardson, and I'm an electronics engineer focused on power supplies. This is the second part in a series of web seminars for power supply enthusiasts who aren't necessarily trained as electronics engineers. In part 1 of this series, I talked about the basic supplies needed to start testing. Now, let's look at some power supplies that don't actively control their outputs. This type of supply, an unregulated supply, is less and less common because it's getting more and more affordable to make regulated power supplies. But we can still learn a lot from older unregulated supplies. In this video, we're going to see where the unregulated power supply can still be found. It's more and more rare to actually find them. Then we'll look at the heart of most of these supplies, which are based on transformers that operate at the AC line frequency, either 50 Hz or 60 Hz depending upon where you live. Since transformers take in alternating current, or voltage, and also output alternating current or voltage, just about every supply needs to be rectified, meaning that the AC is turned into DC. By their nature, unregulated supplies allow their output voltage to change as their output current changes. So we'll test this on some real supplies. Then we'll explore our universal challenge on all power supplies: heat.
So here are 3 power supplies. Right? This one was salvaged from a telephone. My cat decided she wanted to sit on the base and knocked it over so many times that the phone died, but the power supply still exists. Here's one from another phone. The same cat also killed this one. So this is an unregulated line transformer-based power supply. This is a switching power supply. This one is 6.5 volts at 500 milliamps, and this one is 6.5 volts at 600 milliamps. So notice the difference. But the big thing is the weight. If you want to know the difference between a transformer or a line transformer-based power supply and a standard one, you just have to see how heavy it is. Right? This one, 220 grams, and a device that's physically smaller and provides actually more power based on a switching regulator is only 55 grams. This one here is an unregulated power supply that I've made myself, and it's even heavier. Right?
I'm getting ready to test my discrete unregulated power supply here, but before I do, I want to make a very important note about electrical safety. Here at the AC input we have earth, those are the tabs there in brass, and whenever you test with an oscilloscope or most pieces of lab equipment, the negative connection, the silver there that we see of the oscilloscope, is also earth. In fact, here's a connection. So I have my tip there connected, and I'm going to use the testing function here. So if I go over and touch, yeah, sure enough, this is electrical earth. Now the reason I say this is that we cannot connect the oscilloscope, right, its connection is here. We cannot connect this to either of the AC inputs. That would be basically shorting earth to line or to neutral. That would either cause the differential circuit breaker to flip or cause a lot of voltage and current across the probe. It would probably go through the oscilloscope, so you would likely damage something. Another important thing to note, if we wanted to test across both sides of the diode bridge, it would not be possible with this oscilloscope and 2 standard non-isolated probes, because again, if we were to connect one probe here and their probe on the other end of the diode bridge, we would be short-circuiting it. If you're a conscientious, environmentally inclined person, then you take your old, unwanted electronics to a recycling center. But you might still have a bag or a box somewhere with old electronics that you haven't gotten around to recycling yet. Look in there for the wall adapters and find the heaviest one.
Here I have my unregulated power supply set up. I've got my 2 multimeters. This one is going to measure the input voltage. This one is going to measure the output voltage at the output terminals of the transformer. An important note as far as safety goes, you always want to focus in here. If I get it to focus. So this device will go up to 750 volts AC RMS. And this one is safe for up to 250 volts AC RMS. So we're not going to explode or destroy anything. So I'm going to come over here and switch it on. We've got approximately 230 volts at the input, again, AC RMS, and the device says 24 volts AC. We've actually got 27, but that's normal, that's typical. When we load it to its 12 volt amp rating, it should be closer to 24 volts.
In general, the lower the frequency, the bigger a transformer will be for a given power level.
50 or 60 Hertz transformers are therefore big and heavy because they need a lot of inductance to operate at such low frequencies. In comparison, the switching power supplies that we'll talk about in parts 4 and 5 of this webinar series operate at frequencies from about 1,000 to nearly 100,000 times higher, so their transformers are much smaller and lighter. Oh, and cheaper.
The same experiment again, but this time the oscilloscope probe is testing the actual DC output voltage. Here's the multimeter reporting about 38 volts, and what I've done is to take the oscilloscope and put it into AC coupled mode at only 2 volts per division. So you can see here that it's very, very smooth, and that's because there's no load. Now our unregulated power supply is loaded by this 330 ohm power resistor. So from the positive output it goes to the resistor, then it goes into the blue multimeter, and this one is actually measuring DC current. There we can see 93 milliamps. The other multimeter is measuring the DC output voltage. And from the blue multimeter, the voltage returns back to the load. Another important thing to note, now that our circuit is under load, we actually see some ripple. Now I did have to zoom in. This is now 500 millivolts per division, but we can definitely see a difference between the loaded and the unloaded case.
Pretty much all modern electronics run with DC, direct current. So rectifiers are employed to convert the AC outputs of the line transformers into DC. In general, there are 3 things that destroy microchips or electronics. Too much voltage is the first and most common. A negative voltage connected where a positive voltage should be used is a second cause, and that's where the rectifier comes in. The third cause of death is heat, and we'll discuss that towards the end of this webinar and at the end of all the remaining webinars as well. Discrete diodes and diode bridges come with voltage ratings for the peak or DC voltage they can handle in reverse, and they come with current ratings for the DC or the RMS current. In most cases, exceeding the voltage by even a little bit destroys the diode almost immediately, whereas too much current causes too much heat. That can destroy the device, but it usually takes longer.
Here's the unregulated discrete component power supply, but now the diode bridge has been taken out of the circuit and replaced by this single rectifier diode here. At no load, we still have about 38 volts at the output, and we can see with no load, the output voltage is very, very smooth.
Once your AC is rectified into DC, it still has a lot of ups and downs in terms of output voltage, and that gets worse as you apply more and more load. Applying rectified AC directly to most electronics will work sporadically at best, and will destroy your electronics at worst because the peaks of the output voltage can easily be too high and cause overvoltage. A large capacitor, usually hundreds of microfarads or millifarads, absorbs charge while the rectified AC is above the desired output voltage, and then supplies that charge to the load when the rectified AC is below the desired output voltage. With enough capacitance, the output begins to look very smooth.
Here's the half-wave rectifier circuit again, but this time with the 330 ohm power load connected in. Drawing just under 90 milliamps, the voltage is about 30 volts, and most importantly, we can see quite a big difference. There's a lot more ripple at the output voltage now.
After rectifying and smoothing, there's still the droop, or the loss of output voltage as more and more load current is drawn. This is why the outside of the wall adapter says, quote, 6.5 volts at 500 milliamps, unquote. It's been tested to have that voltage at that current, but the average output voltage will rise at lower loads and sink at higher loads. Whatever device is powered by this adapter must either have a steady, constant current draw, or must be able to withstand the changes in that voltage.
Here in this experiment, what I'm doing is testing the transformer at the maximum volt amperes that it's capable of doing. So on the back of it, which we can't see now, it says a maximum of 12 volt amperes. And we know that when we connect it to the line, we have 230 volts RMS. So 12 divided by 230 is about 52 milliamps. And this is as close as I could get with a type of variable load which I have here called a constant linear current source. And you can see this in more detail in part 5 of this series. So I have jumped ahead a little bit to make a point. When loaded to its maximum, we have about 25.5 volts here. And also when loaded to the maximum, you can see that there's more ripple at the output. Now this could be reduced by having more output capacitance, but we can see that the approximately 24 volts that was listed as the secondary voltage at maximum load is approximately correct.
Our basic unregulated power supply consists of a transformer, some rectifier diodes, and hold-up capacitors. Of these 3 components, the capacitors are the most sensitive to heat. To get all the capacitance needed, the type of capacitor used is almost always an aluminum electrolytic. These have a liquid or gel inside, the electrolyte, and over time it evaporates. Once it's gone, the capacitor isn't a capacitor anymore, it's just a resistor. Now, the hotter the air around the capacitor and the more the capacitor heats up from having current pass through it, the shorter its usable lifetime. A lot of electronics enthusiasts are familiar with the term recapping, and this refers to saving a piece of electronics by replacing all the dried out aluminum electrolytic capacitors.
One of the last things I'm going to do is test how hot the different components in my discrete semi-regulated power supply get. So what I've done is connect it to the maximum load. In the previous test, I checked to make sure that we were drawing 12 volt amperes by watching the current at the input. Now I'm watching the current at the output, about 320 milliamps. We can see that the voltage has fallen approximately to the nominal voltage, 25.5 volts in this case. And if you're wondering what was the use of that ATX power supply turned into a lab supply, well, in this case I'm now using it to run this DC fan. Now, I'm not blowing the air on the actual power supply, I'm blowing the air on the load. The load, again, is basically a 10-turn precision potentiometer connected to a linear regulator. It makes a linear current source. But the watts that I'm dissipating here are a lot higher than what it can normally take. So the air is keeping this part cool. Here is my thermocouple, and the tip is just resting in free air right now. You can see it's a pretty hot day here in Spain. Even inside my house, it's almost 30 degrees. So what I'm going to do is grab the tip here, and I'm going to touch it to the tops of different components. So, for example, the actual transformer top is maybe 33, might get up to 33.5 degrees or so. So even at the maximum load, it's not getting very hot. Probably even more interesting is to look at the aluminum electrolytic capacitor. That device is about 32 degrees. So overall, this power supply is not heating up very much at all. The two critical components are only maybe 2 to 3 degrees, maybe 4 degrees higher than the ambient air temperature. And they're also below 40 degrees C maximum listed on the transformer. So there's one other component in this power supply whose temperature I want to measure, and that's the diode bridge that I'm looking at here. Again, it's about 30 degrees C ambient temperature. When I do the temperature test here, I'm going to be very careful because the blue and the black wires we see are connected to 230 volts AC. Definitely do not want to short that with my hand. So I'm going to very carefully put the tip there, and if we come over, it's a little bit blurry, but you can see that we get to almost 39, almost 40 degrees. So this is the hottest component in the circuit.
That concludes Part 2 of Power Supplies for Non-EEs. Stay tuned for Part 3, where we'll look at regulated linear power supplies. On behalf of myself and electronicstutorials.ws, thanks for watching, and we hope to see you for Part 3.